Okay, we're going to see how we can understand divisibility in commutative integral domains in terms of ideals. So let's take R to be a commutative integral domain. Recall what it means to be an integral domain. It means that if you have two elements a, b in R and a, b is equal to 0, then a equals 0 or b equals 0. In other words, you cannot have two non-zero elements of R which multiply to 0. Okay. So one nice thing about integral domains is there is a cancellation law, a multiplicative cancellation law. That is, if you have AB equals AC, then you can write this as A times B minus C is equal to 0. So if A is not 0, then we must have B minus C is 0, which implies that B equals C. So this is just like cancelling A on both sides of the equation, AB equals AC. Okay, now let's define divisibility. So if A and B are in R, we say that A divides B, and we write it with this vertical line just like in integers. If there exists an element Q in R such that B is equal to AQ. Okay, so in terms of ideals, this has a very simple interpretation. A divides B if and only if the ideal generated by A contains the ideal generated by B. Well, the proof is very simple. If A divides B, then B equals AQ. So the ideal generated by B is, well, it's the set BR, R in R by definition, and so this is AQR, R in R, which is certainly contained in A, right? Because A is the set of, this ideal generated by A is the set of elements A R prime, where R prime is in R, and so this is, of course, each of these elements is of that form. And conversely, if B is contained in A, then of course the element B itself belongs to the ideal generated by A, which implies that there exists Q in R such that B is equal to AQ, which implies that A divides B. Okay, so divisibility translates into containment of ideals by this theorem. Okay, now for example, the ideal generated by 2 is larger than the ideal generated by 6. These are all even numbers, and these are all multiples of 6. Okay, that's a simple example. And well, you know that 2 divides 6, or 6 is divisible by 2. Okay, so now a unit in a ring, in the ring R, so an element of R is called a unit if there exists V in R such that UV is equal to 1. Okay, this b is called the inverse of u, okay, denoted by u to the power of -1. So for example, in z integers, the only integers which can be multiplied by another integer to get 1 are plus or minus 1. And in a polynomial ring fx, where this f is any field, the non-zero elements of f, which are constant polynomials, are the units. Because if you have a non-constant polynomial, that means its degree is going to be at least 1, and when you multiply two polynomials, the degrees add. So there's no way you can multiply two polynomials of degree greater than 0 to get the constant function 1, which is the multiplicative unit of the ring of polynomials. So every unit has to be a constant polynomial, and then among those, it's obvious that the units are in fact the non-zero constant polynomials. Okay, now here's thing about ideals being equal. So the following are equivalent. One, suppose I have two elements a, so this is for a, b and r, where we're taking r to be a commutative integral domain. The ideal generated by a is equal to the ideal generated by b. 2, a divides b and b divides a. 3, b equals au for some unit u of r, and 4, a equals b times u for some unit u of r. So if any of these conditions hold, then we say that a and b are associates. Okay, let's try to prove this. It's not very difficult. So we have already seen this from the previous page, that if a divides b, then the ideal generated by a contains the ideal generated by b. So if a divides b, then the ideal generated by a contains the ideal generated by b. B divides a implies the ideal generated by b contains the ideal generated by a. So if a divides b and b divides a, then the ideal generated by b is equal to the ideal generated by a. So 2 implies 1. And now let's prove that 1 implies 3 and 4. So if a is equal to b, or maybe we'll prove that 2 implies 3 and 4. So if a divides b, then b is equal to au, and if B divides A implies that A is equal to BU prime for some elements U and U prime in R. Okay, so we have B is AU and A is BU prime. So we can write it as A is BU but B is AU prime, so BU U prime. AU U prime. Or we can write this as A times 1 is A U prime. And now we can use the cancellation law, which means that U and U prime are units. So what we've shown is that if A divides B and B divides A, then B is A times a unit and A is B times a unit. So we've shown that 2 implies 3 and 4. And so it remains to show that either 3 or 4 implies implies 2. So we need to show that remains to show that, let's say, 3 implies 2. So we start off by looking at if B equals AU for some unit. So if B equals AU, then obviously even if U is not a unit, this means that A divides B. But since U is a unit, what we have is multiplying both sides by the inverse of U, we get BU inverse equals AU U inverse. But UU inverse is 1, so this is equal to A. So BU inverse is equal to A, so that means that B divides A. So this completes the proof of the equivalence of these 4 conditions, and these are 4 different characterizations of associates. So what this answers is, when do 2 different elements generate the same principal ideal? So 2 different elements generate the same principal ideal if and only if they are, by definition, if and only if they are associates. And this means that they each can be obtained from the other by multiplication by a unit, or each of these numbers, elements of R, divides the other. Okay, so let's look at some examples. So a very interesting example comes from the polynomial ring R equals QX. Okay, so let me ask, what is the ideal generated by x minus 1? Okay, take any field here, it doesn't have to be Q. So I claim that this has a very geometric, I don't know if you can call it geometric, but a polynomial thing. So it is the set of polynomials fx in Qx such that f of 1 is equal to 0. So why is this the case? So I want to show that these 2 sets are equal. So let's show that, so suppose, what is the left hand side? So this is equal to the set of all polynomials of the form x minus 1 times gx, where gx belongs to qx. Right? But any polynomial of this kind, if I take fx equals x minus 1 times gx, then f of 1 is 0 times g of 1, which is 0. So this thing is contained in the left hand side, is contained in the right hand side. More interesting is, why should any polynomial which vanishes at 1 be divisible by x minus 1? And here Euclid's algorithm comes in, division algorithm. So what does Euclid's division algorithm say? It says that if I have a polynomial fx, I can write it as qx times x minus 1 plus rx, where the degree of rx is strictly less than the degree of x minus 1. But the degree of x minus 1 is 1. So that means that this degree of rx is actually 0, which means it's a constant polynomial. So it's, in fact, I can just think of it as R in, well, I was working with Q, but yeah, I can work with any field here. Okay. Now this is true for any polynomial. Now if f of 1 equals 0, then we must have, substituting x equals 1 on both sides of this, we have q1 into 0 plus r is equal to f of 1, which is equal to 0, which implies that r equals 0. So that means that x minus 1 is divisible by fx. So, but that's precisely the definition of the ideal generated by x minus 1. It's those polynomials which are divisible by x minus 1. So this is equal to, so this means that f belongs to LHS. And so what we've also proved is that the RHS is contained in the LHS. Running a little short of space here. Okay, so there's a nice way to understand ideals. This is more general, of course, that if you have the ideal generated by x minus a consists of polynomials which vanish on a. And this is an ideal theoretic incarnation of the factor theorem for polynomials. So the factor theorem for polynomials says that a polynomial is divisible by x minus a if and only if it vanishes at a.